So hello, it's me again, Zulfan, and now last time we have discussed on how to solve unconstrained optimization with one variable. Now we are going to solve how unconstrained optimization with multiple variables, more than one variable. Yeah, so by the end of today's class, we will then finish the whole part of um, the first part of the course. Like in the previous one, so we have like a derivative based method and a non-derivative based method. So in this case, we also have the same thing. So derivative based method, the non-derivative based method, we call it direct method because we directly calculate the objective functions from the variables. And then the derivative based method, we call it indirect methods because we do not calculate the objective functions directly. Yeah, we use their first derivative and second derivative in the case of Newton, and then we don't use any of the derivatives in the finite difference Newton, and we only use the first derivative in the second method. So we'll discuss first on the direct methods. Yeah, the most famous one is a simplex method or Nelder method, and then for the indirect methods, the most famous one is then obviously the Newton method. So, but we will see the other methods as well, just to give you a feeling. So the general procedure. So assuming that this and we have like a contour plot, and then it's pointing towards us. So we have imagine that we are that blind person. So our control is only the step size and also the directions. The step size, how far we are, and then and the second one is either we are moving in these directions or in that directions. Yeah. So the simplex search, it's basically we start with if we assume that we have like two variables, yeah, to simplify this, two variables x1 and x2, and then in this simplex method, we need to specify, or we have to have like three different locations of x1 and x2. Here we have like a, b, c. So in point A we have x1a, x2a. In point B we have x1b and x2b. In point C we have x1c and x2c. So we have three pairs of x1 and x2 at three different locations. And then we just evaluate what is then the so in this case we could also make this kind of algorithms. So we have only like point A, and then with this algorithm you can calculate point B and point C, but you could also make your own point B and point C. And then we evaluate how much is the FA, FB, and FC. If we want to minimize these functions, so we will then, if we evaluate, we can see now which one of these FA, FB, and FC is then the minimum point. Is then the maximum point, sorry, and then that maximum point we have to remove and then replace it. For example, in this case, if FA is then the giving us the maximum, for example, FA is then 10, FC is then the 5, FB is then the 6, for example, and then 10 being then the worst case, being then the maximum. Since you want to have the minimum point, so we have to replace A. So we remove the A and then develop an algorithm to change A to the new A. Yeah, hopefully with the new A we'll get a value that is then lower than both B and C. So in this algorithm we have we just use a simple calculations to get the new A. So delta is then the centroid of B and C, half of B plus C, and then the new value of x1 and x2 in new A, and then this 2 delta minus the old A. Yeah, so x1 is then 2 delta minus old x1a, x2a new equals to 2 delta minus old x2a. And then we keep it going until we converge to the yeah, we have the convergence situations. So we can visualize like this. So we have x1, xa, xb, and xc, x0, x1, and x2, yeah, and the variable x1 and then the variable x2. So since we want to, like, for example, we want to go into these directions, and we start from here, so we know then we can see that there's a different contour, either maximum or minimum. So take this, if this then the maximum, so this then it has number, this contour is then higher, has a higher number than this this line, that is becoming higher and higher, and this becomes like the highest point. So this obviously being the lowest number, so we replace this with a new x0 over there. This has a higher number than that number, right, based on the contour, and this becoming the lowest, so we remove this and then we put it in the new number over here, and so on. This becomes that, this becomes that, and so on and so forth until we get this x9. So the 9, like this is 9 point, yeah, not the 9 iterations. So if I put this in Excel, so we have this lambda following that, following the previous this algorithm, I put it in Excel. So x1, I start x1 and x2 equals to 1 and 1, minimizing this. Calculate the two variables, calculate the delta, and calculate the b and then the c point. So for this point A, we get fa equals to 0, point B, fb equals to 0.54, fc equals to 0.3. So since we want to minimize it, so that we know that fb is then the highest point, so we have to replace b with a new b. So we keep a constant, so 1 1 constant 1 1. C is also constant, that number and that number stays constant, and then the b, we have to change it with the algorithm. So we change x1b from 1 to 0.9, x2b from 1.02 to 1.07, yeah, and then we now having b as then the minimum point. Now in this case fc is then the maximum point, so we change the fc into into here, minus 0.4. So the procedure continues until all of this fa, fb, and sc is about to converge to minus 3 in this case, yeah, and then all x is converging to close to 0.1, 0.1, 0.07. So it's all like converging to 0. So if we know that, because this is a very simple example, if we put x 1 equals to 0, x2 equals to 0, that makes the minimum value of fx, which is then minus 3. This is another variant. You can also go through the slide. It's just a matter of different algorithms to calculate the new x, yeah, and then same. And in this simplex, in this first two, there will be 3 different scenarios where you are like straddled. If the selected was vertex, right, was generated in the previous iteration, so if we see this vertex already generated in the previous iterations and we cannot move further, and then we have to then select the next worst vertex to be changed, so that we are not stuck in that region. Yeah, and then if it doesn't change, number 2 is then if the values doesn't change after a number of iterations, and then we can just try to reduce the some factors of your calculations, like in this delta, or some rule to change the new value to a smaller deviation, so that we're not stuck in that situations. And then if the simplex gets small enough, so if the value is then close to or lower than our tolerance, we can then search terminate the search. Nelder-Mead algorithm is the most famous one. So in the previous simplex, it's only like we have the B and C, and then the new A is then only the centroid. Yeah, and then the mirror, as you can see. But in this Nelder maze, instead of only mirroring that, we have or reflecting that, we have additional terms. These are then we have the new we have the 3 points, and we calculate the functions. Yeah. So yeah, it depends. How many x variables you, how many pairs that you would like to have. It's all up to you. You can have 3 or 4 or 5. It's all up to you. And then you can then evaluate the functions of each pair, and then order them in such a way that we have the in this case it's in the ascending order. So fxn plus 1 is then the highest value. So and we want to minimize it, yeah. So that means we want to change this fx1 n plus 1 into a better value. So calculate centroid, and then the previous two approaches only reflection. So we have then the old one and then the new one, and then a bit not only reflections, we could also have like expansions. So the old one, and then this is the reflected one, but we could also expand it depending on the situations that we have over here, which you can read. And then we could also have like contractions. So instead of this the old one, the reflection one, the reflected one, and then this we contract it a little bit. So this then the new x, yeah, depending on these conditions. And then we could also then shrink the whole 3. So instead of only changing one, you could also shrink them like this. With this if we have these conditions, if these conditions apply, and the whole constant like alpha, omega, rho, and then delta are the constants of reflection, expansion, contraction, and shrink respectively. These are then the typical constants that we can use. You could use your own constant as well. So this is then the Nelder-Mead algorithm, how it works in practice. You can see. You can see that. So you can see how it moves. So that's actually the simplex method. So the size is different from time to time because we have different we have many criteria on how to reflect, expand, contract, and then shrink. If we put that in MATLAB we have the code is called fmin search. So this Nelder-Mead algorithm is coded already in fmin search functions. So we have the functions of 2x1 square plus x2 square minus 3. So the same functions, same example. We start x1 equals to 2, x2 equals to 2, and then we run the code, and we get so it is the objective function is the minimum objective function is minus 3 as we know it, yeah. And univariate search method, it's more like if you see this, so we change only x1 in this case from x0 to a certain value while keeping the x2 constant, and then at this point we keep the x1 constant and then change the x2 based on a certain step that we define. So you can make like a bigger step like this or a smaller step like this one. So that is then the basic for this univariate search method, which is also the Powell method later on. Yeah, you can see. So depending on the delta, you can calculate from your initial points, and the delta you can calculate the new f. Like in this order, you can see that's now going down and down until it will then go to minus 3. But be careful, you could also jump over this minus 3, and you don't see this minus 3. And in that sense, you can then reduce the step size from 0.2 to 0.01 or something. like in this case. So if you don't, depending on the step value, you might either see this or not see this. But if you see that this is then already approaching to a minimum, this is then no longer approaching to the minimum, so that means this is going to be your new range. Yeah, the conjugate search method, I think you could read this on your own. Yeah, the slide is online. So I have made some examples on how to calculate that. What I would like to point out is that all of this is, we don't need to find or use the derivative functions, yeah, because many functions out there that the derivative is very difficult to have, or it's very time consuming. So we can better use either of these direct search method, with neldermid being the most famous one. Yeah. This is then the Powell's method with this algorithm, which you can read as well, and some examples that I left for you. Now we shift our focus to the indirect method, which is based on the Newton method. So the same case with the one variable. So in here we use also the first and second derivative, and then in some cases numerically it's going to be very difficult to find the second derivative. For the first derivative it's easy, so you can just change the delta x, yeah, change the variables a little bit and then calculate the functions. There you can get the first derivative. But the second derivative, sometimes it's difficult numerically if we have like complicated functions. So in that sense, we have other methods or other approach to other tools to approximate the Hessian matrix or the second derivative. So BFGS, as in the second method, is one of the modified Newton method, as you will see later on. So in the same case, we start with the initial points. We calculate the functions, the first derivative, and then the second derivative, which is then the Hessian matrix. So we know that the delta x, yeah, the delta x is minus the first derivative divided by the second derivative. So I put it here in terms of a matrix. So minus the inverse of the second derivative multiplied by the first derivative. And then this is then our delta x, and then this delta x, we add them into the old x. So you get the new x equals to the old x plus delta x. Yeah. So in here, if you expand this a little bit, so this makes 0 minus first derivative divided by the second derivative. It's all the same, as you can see over here. And then we repeat the step until we meet the convergence criteria. So you can see the Newton method. So the same functions all over again. So x0, we start from 1 and 1. We put this number in here. So we get 2 times 1 is 2, plus 1 is 3, 3 minus 3 is 0. And then the first derivative of this guy is then, if we derive it to x1, so it's 4x1, which is this. If we derive it to x2, which means 2x2 is 0, 0, 2x2. So this is then first derivative of f to x1, the first derivative of f to x2. And we put this number into here, so we get the gradient of f. The first derivative is 4 and 2 in this case. And the second derivative is then the Hessian matrix of this. So we derive this to x1 again, that makes 4. And then we derive this to x2, which is 0. And the next row is then we derive this into into x1, that makes this 0. And then we derive this into x2, that makes 2. So 4, 0, 0, 2 is then our Hessian matrix. And then from here we calculate the delta x. We calculate delta x in this way. So we get delta x1 is minus 1, delta x2 minus 1. And we get the new x1 is then the old x plus delta x. So 1, 1 plus minus 1 minus 1 equals to 0, 0. And this, if we plug this back into our equations over here, that makes minus 3. So if we use this number x1 equals to 0, 0, we go back to step 2, we calculate, put this 0, 0, and then delta f is also already 0, 0, and then this is a constant, and that 0, 0, you plug in that back to here, so you'll have that delta x equals to 0, and you will then be yeah, that means you meet your convergence criteria where delta x is already equals to 0 and your new x doesn't change anymore. That's the Newton method. And this Newton method works perfectly in smooth system, yeah, where we know that the first derivative is continuous, and then it has the fastest convergence if we work the second order like we know it. But sometimes if we start at x0 is far from the optimum, for example, if we have this function and we start somewhere here, and then this function is complicated, not as easy as this one, it will become difficult for Newton method to find it. And then sometimes it's hx is single at some point, so that means this determinant is 0, and that is difficult to solve, or it cannot be solved. Like I said, if we have difficulties in finding the second derivative, we can have like a quasi-Newton method where this Hessian matrix is approximated by some approximations, this B. So this B, there are many methods like DFP, BFGS, Broyden family, SR1. So this is then they have the Hessian matrix approximated by this formula, which you can use either one. Yeah. So in this case, the Hessian matrix is updated every time. So our initial BK, in this case, BK. So the initial point, it could be any Hessian matrix you can use any number. But most people use identity matrix. Then you can update that in the next iterations. But the point, the general algorithm is the same. So we have the initial points. We calculate the first derivative. We calculate the second derivative. In this case, the initial point of Hessian matrix, and then we get the new delta x, and then we calculate the new x, and then we calculate the new Hessian matrix with any of these formula. Yeah, same approach. These are the algorithm. BFGS, if you use BFGS in MATLAB is coded already in fmin unconstrained UNC. So you can see that for the same value, it converges already in 2 or 3 iterations to the value of -3. So instead of, compared to Dandelmit, we have much more iterations, and this BFGS, it's converged within 3, 4, yeah, somewhere here, 6 even, converge to the solutions. Gradient method is the same. It's just like it starts the Hessian matrix with the identity matrix. Yeah, you can see this, and you can see this. Yeah, all in all, indirect method has been proven. Indirect method means the derivative-based method. It has been proven to be more efficient because we need only like several iterations, as you can see when you compare the BFGS and the Dandelmit. And then for things functions that we cannot derive, we can either use the approximation of the Hessian matrix, or we can better straightforward using the direct methods like this Dandelmit. So that is all for this lecture. So see you next time. Okay.